Hi, welcome back to AP Physics C Mechanics. Again, we're still in our journey of kinematics. So this is topic 1.4, I believe. 1, 2, 3. Yeah, so this is topic 1.4. This is reference frames and relative motion. So in the first video, we talked about that vector notation. So a lot of times this is where you're going to see that in some of these questions. Okay, so the choice of reference frame will determine the direction and magnitude measured by an observer in that frame. Measurements from a given reference frame may be converted to measurements from another reference frame. So pictorially, right? If I'm on a train and I'm throwing an object up, I see the ball going straight up and down. But at a station, right, at a platform, the observer is going to see the ball traveling in a parabolic path, because what they now see is not only that vertical motion, but that linear motion of the train. Okay. So the observed velocity of an object results from the combination of the object's velocity and the velocity of the observer's reference frame. So combining the motion of an object and the motion of an observer involves the addition or subtraction of vectors, and the acceleration of any object is the same as measured from all inertial reference frames. But something also to note is that even though this talks specifically about velocity, this also could apply to acceleration. It could also apply to position. Okay, so if you look at just a simple example, train A is not moving, B is moving. So if you're looking at it from train A or the platform, B is what's moving, right? And so they're traveling in a positive direction. And now if you look at it in terms of train B, they see A or the platform moving away from them. So what they see is actually train A or the platform traveling at a negative velocity. Okay. So again, this is, that example is linear, but you can also have, if I have something moving kind of in this manner, right? And this is object A, and this is object B. What does that look like, right? In fact, we're going to do that because in the last video, we had a cat and dog, but our example is going to involve the same cat and the same dog. However, they're going to be moving in kind of opposite directions, as in the X and Y direction. All right, so here we have a cat passing a dog traveling in a positive X direction at 5 meters per second. As the cat passes the dog begins to accelerate at 0.5 meters per second squared in the positive Y direction. Now, part A, what is the cat's acceleration relative to the dog? Part B, what is the cat's velocity relative to the dog at time t equals 5 seconds after the dog begins running? And then what is the cat's position relative to the dog at time t equals 5 seconds after the dog begins running? All right, so the way you think about it, the acceleration of the cat to the ground, right, is 0 I hat, right? Because they're traveling in the X direction. The dog to the ground is 0.5 meters J hat, right? Because they're traveling in the positive Y direction. So essentially what we need to do is kind of subtract out that ground, okay, from so A cat dog is going to be 0 I hat minus 0.5 J hat, okay? And so this is the acceleration of the cat in regards to the dog, right? Because in fact, remember the dog is running at it, but the cat is kind of running away from the dog. So that's why it's moving. It has a negative acceleration in reference to the dog. Now, part B, what is the velocity of the cat? Okay, so we're going to do V cat, right, plus our acceleration of cat dog. Okay, and so the velocity of the cat with respect to the dog, it's moving, right, initially. The dog is not moving, right, plus our acceleration, which is our answer to part A. And we're going to look at that after 5 seconds. So the velocity of the cat relative to the dog at 5 seconds is going to be kind of this combination of vectors, right? So we can't do anything here. In fact, I'm going to get rid of that j hat from our initial velocity. Now I multiply 5 by everything here. Well, that's going to be 0, right? I hat minus 2.5 j hat. And so what is the velocity of the cat with respect to the dog after 5 seconds? Well, it's going to be 5 I hat minus 2.5 j hat meters per second. And I forgot my meters per second squared here because that's our acceleration, right? And so you can see how I wrote that with the unit. Right? I got 5 I hat minus 2.5 j hat meters per second. You can also write like 5 meters per second I hat minus 2.5 meters per second j hat, whatever's comfortable for you, okay? Now, what is the position of the cat? So we need to find delta R, right? Because we're not looking for its displacement, right, by itself. We're looking for its position relative to the dog. So we're going to use our position equation. So V cat dog T plus 1/2 acceleration cat dog T squared. So I kind of do the same thing, but instead of, now I've got to plug in all this stuff, right? So I have 5 I hat minus 2.5 j hat times 5 plus 1/2 0 I hat minus 0.5 j hat. Sorry, I ran out of space here. 5 squared. So 5 times 5, right? Multiply all that out. So delta R is going to be 25 I hat minus 2.5, which is, did I write it down? Oh, sorry, that's my initial velocity. I apologize. So this for the dog is 0. Right? So that's going to be 0. It's not k hat. That's not the z direction. Dog's not moving off the ground. So plus 0 j hat. And I do plus 0 I hat from our acceleration piece, 1/2 times 0 times 5 squared. And now I have 1/2 times negative 0.5 times 5 squared ends up being 6.25 j hat. So these I don't write. So delta R is going to be 25 I hat. Now, if you think about it, does it make sense that it's moving, it's moved 25 meters? Because, 5 times 5 is 25, right? Now, what about the dog? Where's the dog's factor come in? Well, it comes in because the dog is accelerating, right? So that's where we get the negative 6.25 j hat. So basically what's happening, if this is our initial position, right, the cat on its own has moved 5 meters this way, but what happens is, the dog is moving this way, 6.25, okay? And so that's what the cat's position relative to the dog. So it's kind of moved in this direction, right, according to the dog, right? And we don't have to find the magnitude of it. Sometimes you would have to do that if it says what is the magnitude of the position vector. But this one is just asking for what is the cat's position relative to the dog, okay? If it says what is the magnitude or what is the displacement it traveled, relative to the dog, then you would say 25 squared minus or plus negative 6.25 squared. Take square root of that to get the magnitude. All right, so that's going to end our conversation about reference frames and relative velocities and so forth. The next video is going to finish the unit, and we're going to talk about when, kind of more of this multi-dimensional motion.